So let's look at this question that involves a rectangular area which is going to be enclosed by this 100 meters of fencing. But it says that there is going to be a border on one side, so we don't actually have to enclose that side of the rectangular area. I want you to look at the diagram over here on the right, which shows is a representation of what we're talking about. We have a wall on one side, and then we have a width, which is represented by x, and a length, which is represented by y. So let's put some let statements together. So we're going to let x represent the width and y represent the length. Well, if you think about it, since all of these lengths have to add up to 100, we can represent that algebraically by saying that the x plus the y must be equal to 100. Well, what if we turn that into a y equals, isolate the y? We would end up with y being equal to 100 minus 2x. And the reason we're doing that is because we want to set this whole thing up in terms of x alone. So if I just made a substitution in a new diagram, instead of putting this y here, I'm going to put what y is represented by, which is 100 minus 2x. So look at the side over here, now labeled with not y, but 100 minus 2x. So we have a diagram which is in terms of x exclusively. Well, we can now come up with a formula for the area of this diagram or of this enclosure. They asked us to find an area in terms of width. That's what the first part of the question says. So we know that area is equal to length times width. So here's our length, 100 minus 2x, and here's our width, which is x. So these two things multiplied together represents our area. So we've actually answered the first part of this question. There's our area function in terms of the width. Well, now we have to answer the question of domain and range. Before we get to that, let's just recognize that this is actually a quadratic formula. If you were to multiply this x into the bracket, then you recognize that you're going to end up with an x squared term. Here's our x squared term right here. And that tells us that this is a quadratic function. So we now need to try to represent this on a graph for us to understand. All right, so here's our formula again. Our formula for area is area equals x times 200 minus x. For us to draw this, we probably need to find where the zeros are. It's in factored form right now. I want you to remember back in grade 10 when you wanted to find your zeros, you would take your formula and you set it equal to 0. Let's solve this now. There's a rule in math called the zero product law where these two things are multiplied to give us 0, which means that both of these can be set equal to 0. So let's put each one on either side of this line. I'm going to take this x and set it equal to 0 on its own. Then I'm going to take this 100 minus 2x and set that equal to 0 on its own as well. And we're going to solve both of these. Well, this one doesn't need to be solved. This already says that x is equal to 0. That's one of my zeros. On this side, if we solve this for x, we're going to end up with that x is equal to 50. So we now have our two zeros. One zero is at 0, and the other 0 is at 50. Remember, whenever you want to figure out where zeros are for a quadratic, just set it equal to 0 and solve for x. And it's always better if it's in factored form, which is exactly what we just did. So let's put this on a graph. Here's our graph, which is represented by width on the x-axis and area on the y-axis. And here are our two zeros. One is at the origin, 0 itself, and the other one is at 50. So I guess the next thing we have to decide is how do we actually draw our graph with these two zeros? Remember that a quadratic function is a parabola which either opens up or down. So we have two choices. It could either open up like this or it could open down like this. And if you remember back in grade 10, the way we could figure out which one it was by looking at the coefficient of the x squared. So look again at the formula that we had. This is when we put the formula in standard form. We had this on the previous slide. So in standard form, we have 100x minus 2x squared. We look in front of the x squared. We have a minus 2. That tells us that our function actually, or our parabola actually opens down. So it must be this one here and not this one that opens up. So let's just look at the one that we're focusing on, the one that opens down, which would be this parabola right here. Well, now that we have a picture, let's see if we can come up with the domain and range, because that's really what this is all about. Domain. Consider your x-axis for your domain. What values of x are possible on this graph? Well, normally, if we're looking at a parabola, we would say it's all real numbers. You could go anywhere along this x-axis and the graph would exist. The graph goes all the way down here and goes across. But let's be practical. If this represents width, which is what this x-axis represents, then in realistic terms, you can't have an x value lower than 0, because once you go below 0, you're now in negative territory, which means you're talking about a width which is negative, and that's just not possible. There's no such thing as negative width. So the lower end of our domain has to be 0. Well, what about the higher end? Can I have a width which is bigger than 50? Well, if I put 50 into this function right here, which is what we started off with, 100 minus 2 times anything which is more than 50 is going to make this part become negative. And in fact, just looking at the graph, we can tell that once we go beyond 50, our area, this is our area line here, drops below the x-axis, which means that my area now becomes negative. So again, that's not practical. It does tell us, therefore, that our domain must only go between 0 and 50. That is the limit on either end. It's no lower than 0, no higher than 50. And therefore, a domain is XCR. X is all real numbers, but X has to be less than 50, but greater than 0. Notice that I didn't say greater than or equal to or less than or equal to, because it cannot be equal to 0 and it cannot be equal to 50. At those 2 points, I would have a 0 area. I'm going to be at 0 on the area axis here and 0 at the area axis here. And a 0 area, again, makes no sense. So it means that my domain must be between 0 and 50, but not including 0 and not including 50. The highest it can be is 50, or just less than 50, and the lowest it can be is just more than 0. Let's consider range now. To get our range, we have to look at our vertical distance. How far up does our graph go? How far down does our graph go? So again, it makes no sense for us to consider area values less than 0, because when you're talking about area, you cannot be talking about something that's negative. So it tells us that our range starts at 0. That's the lower end of the range. But how high does it go? Well, if you think about it, it has to be as high as this point at the top of the graph where my arrow is pointing. And we used to call that back in grade 10 the vertex of the graph. So we need to find what this vertex is. What is the value on the y-axis? And maybe we can read it off, but let's do a little algebra to figure out what this is here. How do we normally find our vertex? Back in grade 10, we learned that we could actually find the vertex by using the midpoint of the 2 zeros. Well, here are my 2 zeros, 0 and 50. So the middle of that, of course, is 25. That's 50 plus 0 divided by 2 is 25. So at 25 on the x-axis, I have my vertex. This axis of symmetry here that splits the parabola in two represents the point at which I have my vertex, or the line along which I have my vertex. My vertex is along the line somewhere up here. For me to figure out exactly what the y value is, or the area value is at that point, I just have to stick this 25 into the formula. So that's exactly what I'm going to do. I put the area of the vertex, area at the vertex rather, is equal to 25, putting it back into this formula here, putting 25 in for x, times 100 minus 2 times the 25, which is my value of x. And that, of course, works out to be 25 times 50, or 1250, 1,250. So now we know how high this thing goes. And you can kind of read it from the graph. It's right over here between 1,200 and 30. And because that's 1,250, we now have our range. Our range is from 0, that's my starting point, all the way up to 1,250. So there's my range right here. YER, as usual, y is an element of the real numbers, but y has to be greater than 0 and less than 1,250. Again, not equal to on either side, it's just greater than and less than. And that represents my range.